So welcome everyone for the next session on regenerative braking. So I think we have seen all these component level explanations, component level discussions on motor, battery, inverter, DC-DC converter, and the thermal management obviously. And one more thing that the one of the topic which is very least very in a very least level it is discussed in the research context is the regenerative braking. So, in my opinion, I'm seeing very few people, working in this particular area. But I would say this is a very good area to work on because regenerative braking has a potential to improve the efficiency of overall efficiency of electric vehicle up to 25%. So it is a very big potential for it is definitely a good contribution that if it is a efficiency of regenerative braking is further improved. And obviously, yes, but currently the situation is it is not considered as very effective way to improve the efficiency of a system. Sometimes in some cases it has become a disturbance as well, right? So here let us understand the regenerative braking system with a small case study, and let us see whether this regenerative braking is a favor for the electric vehicle efficiency improvement, or is it a disturbance for the driver or the passengers who is sitting inside a vehicle. Let us understand that whether it is providing a favor for us or it is a disturbance in the environment, basically. When we look at the vehicle configuration, right, the vehicle configurations available in the market. So this is how basically the components are located, as everyone know. And at the wheels, we have the wheels and the brake components sitting in the wheels, right? Say for example, in this case, the left one, if you are taking this pure electric drive operation, we have the motor. So this is the motor component, and we have a sprocket, drive sprocket for the belt driven operation. So you can see that when the motor operates, this is the way. This is taken from the Aether 450 model, and you can see that this is the belt drive being applied in the Aether 450 vehicle, right? So basically, whenever the brake, whenever a vehicle attains a braking condition, immediately there is a lot of available energy. That is generally in a petrol diesel vehicle, that energy is wasted in the form of heat. So in electric vehicles, since the electric motors have the ability to function as a generator, right? Motor cum generator. So this braking energy, instead of being used in a wasted as a heat, this is also being recovered by the electric motor. So the recoverability, the ability of the electric motor to recover as much as energy from the braking system depends upon multiple factors, right? So we are going to talk about that in detail in the upcoming session, in this particular session. So when we look at a conventional, whenever we take a electric vehicle, basically there are two brakes available in the electric vehicle. One is the conventional service brakes, conventional service brakes that are there always, that should be always there at any point of time. And in addition to the service brake, we also have the regenerative braking. So we also have the regenerative braking, which is also playing an important role in the EV. So when we look at the conventional brake system, I think people might be very well aware about the brake system components. So these are all the brake system components, for a conventional, even for an electric vehicle, the components remain same. So we have a front disc brake for the front disc, and we have a caliper, and we have a brake hose, connecting union pipe, and we have a brake pipe which is actually connecting the master cylinder. We can see the master cylinder is sitting here, and here is where our brake pedal is there, right? So when the driver presses the brake pedal, immediately the brake force, the pressure, the amount of force is exerting, that is boosted by this component called brake booster, which is sitting here, servo unit, which is actually boosting the amount of force applied by the driver, and then the force is applied to the master cylinder, from where the oil with the high pressure is being pressurized and it flows inside the pipe and to the hose and then to the caliper, and then the brake is applied, right? The same master cylinder can distribute for front as well as rear brakes, and you can see the line. This is how the brake distribution is there, and we have something called a brake force reducer modulator, we can say, so which can which can vary the amount of brake force for the front wheel and the rear wheel according to the requirement, right? So according to the braking condition, some amount of percentage of force will be given to the front wheel, and some amount of percentage of force will be given to the rear wheel. Not all the four wheels will not have the same pressure. Depending upon the vehicle speed, depending upon the driving condition, the amount of brake percentage will be decided by the control system, right? So this is the current scenario of the conventional braking system, disc brake, hydraulic disc brake system, right? So right now we have this electric vehicle, we have this additional regenerative braking system, right? So what is the major challenge? What is the major focus of research in regenerative braking? Is nothing but bringing the best customer driving feel. So when there is a braking scenario, there are many chances. I will talk about the different types of regenerative braking. But whenever we apply brake in an electric vehicle, either the regenerative braking functions first, or either the conventional braking system functions first, or sometimes both the braking system functions together, right? So there are many different ways the regenerative braking functions. So the challenge, end of the day, what is the need? What is the need? The need is, one of the need is to recuperate maximum energy from the braking system, from the braking condition. That is the first. That is one of the important aim, the motive for having a regenerative braking, to recover as much as energy as possible from the system. And the other important requirement is basically, the much more important, I would say, is maintaining the or meeting the braking requirement. So if the vehicle should stop in next 5 meter, then yes, it should stop with 5 meter. I cannot say that no, if we need to have a regenerative braking, it will take 10 meter. No, the vehicle should stop in that 5 meter distance as defined. And in that 5 meter distance of the braking situation, either we can use regenerative braking or conventional braking. But end of the day, the vehicle should stop. That is a very important motive. For the purpose of regenerating more, we can't extend the braking, right? It is a safety critical component, right? So being a safety critical component, the braking stopping distance, stopping time, that cannot be compensated, that cannot be compromised for the purpose of generating more power from the brake system. So end of the day, a good regenerative braking system is in such a way that in a very short span of time, or whatever the limited available time, the system should be able to recuperate more energy. So that is the very important requirement of a regenerative braking. At the same time, it should not create a disturbing feel to the driver or the passenger sitting inside the vehicle at any point of time. So the braking system design, the algorithm or the strategy that we develop for a braking scenario should be in such a way meeting all these mentioned conditions. At the same time, we should be able to recover as many energy as possible. That is much important. So when we look at the disc brake, basically we have a caliper. So this is where the hydraulic oil is coming here. The pressure is applied and the pistons move. This is the black color component is the piston, so which actually moves that. And the brake pad, you can see the brake pad touching the coming and touching the brake disc. So here is where the when the brake pad and brake disc come in contact, there is the amount of energy wasted in the form of heat because of the friction, right? And this energy is basically utilized in a regenerative braking. This energy is utilized to run the electric motor in the generator mode and recover the electricity generation from there to the battery pack. So that's the condition. So let us understand how a conventional service brake system can, in combination with a regenerative system, can function, and let us understand what are all its capability, the regenerative braking system capability. Before going to this system further, it is very important to understand the legislative background behind regenerative braking. Many times people think that, okay, regenerative braking, yes, when we apply the brake, it is generating, but it is not like that. There is a legislative background for that. There is a legislation coming from Economic Commission of Europe. The regulation number is 13H and 13.11. And these regulations talk about what are all the ways a regenerative braking can function, what are all the limitations for a regenerative braking, what should not be done by a regenerative braking, what can be done by a regenerative braking. All these limitations are provided in this regulation. And they have very clearly categorized the regenerative braking into different category. So category A, it means what? The regenerative braking is not part of the main braking system. For example, use of a throttle off braking. What is this? So whenever we leave the accelerator, right? Whenever we leave the accelerator, what happens? It leads to deceleration, correct? So when we leave the accelerator handling, immediately the deceleration will start. The vehicle will start decelerating from certain speed to down. It will come down to the lower speed. So this is basically during this time, during this deceleration time, there will be obviously a regeneration happening. So we call it as throttle off braking. So because of leaving the throttle without pressing any brake pedal or anything, just by leaving the throttle of the vehicle, we are able to create a deceleration. So a regeneration happening at this point of time is not part of the main braking system. So it is categorized as category A. And in category B, we have it as phased and non-phased. Means the regenerative braking exists as part of the main braking system, but the regenerative braking torque can be delivered together with the friction braking torque or slightly later. Is it clear for everyone? The regenerative braking torque can be delivered either together with the friction braking torque or slightly after the conventional braking. But a category B phased condition means the regenerative braking torque can be deployed before the friction braking torque. So these are different categories that are covered by the Economic Commission of Europe regulation 13HN 13.11. So end of the day, if the vehicle is having a anti-lock braking system, so the ABS must control the regenerative braking. If the ABS wheel speed signal sees excessive slip, automatically it will typically trigger the suspension. It will stop the regenerative braking. Everything depends upon one of the important factor that decides the regenerative braking function is the slip. So the wheel slip, we call it as wheel slip. So have anyone worked previously anything related to anti-lock braking system?
It is the ratio of vehicle speed to the wheel speed.
Hello?
It is the ratio, slip is the ratio of wheel speed and vehicle speed.
Yes. So is there any faculty already working in ABS or have already known about ABS? Anyone closely working with ABS system? So basically, what is the purpose of using ABS, anti-lock braking system?
It has to prevent, it is to locking of wheels.
Yes. So it is basically to prevent the locking of the wheels, the wheel lock condition, right? Instead of wheel locking during a braking condition, there will be a multiple time. If for example, for a brake event, for every few seconds, few milliseconds of time, there will be a brake application. Brake on, brake off, brake on, brake off. So like this, the brake, instead of a single time brake application, multiple times the brake will be applied and removed, applied, released, applied, released. So this is what we call it as anti-lock braking system, right? And the challenge is the regenerative braking, as we see that it is category A, category B non-phased, and category B phased condition. The first one is throttle off braking, just by leaving the accelerator, how the regeneration happens on the vehicle. Second category, the category B is split into two cases. One is phased and non-phased. So non-phased means the regenerative braking can be delivered together with the friction braking torque or slightly later after the friction braking torque, right? And if it is phased condition, it can be deployed before the friction braking torque. So this is a very important thing we need to understand before going further into the topic. So I think some audience can, some participant can mute your background. Mr. Sudesh, could you please mute your mic? Yes, thank you. So when you look at the regenerative braking system and control, here we have taken an example benchmarking from one of the manufacturer. So basically, there are two types of regenerative braking control. One is serial type of regenerative braking control. One is parallel type of regenerative braking control. So let us understand both these conditions. You can see the left one. This is the parallel type of regenerative braking, and this is series type of regenerative braking. So here in this case, what we do, look at the first case. First regeneration happening is compression regeneration. Means compression regeneration means with just leaving the accelerator. By just leaving the accelerator, what is the amount of deceleration energy required or the deceleration torque gained? And after this condition, then the service region driven axle will apply. That means the brake pedal will be pressed. But in this case, regenerative braking will function because of the frictional effect between the system, the braking force, and all this thing. The service regeneration brake axle will function, and then additionally, parallelly, what will happen depending upon the amount of deceleration torque required, right? Say for example, if there is a requirement torque of 40 Newton meter, right? And if 40 Newton meter torque cannot be provided by the regenerative braking system, right? In that case, additionally, parallelly, what will happen? Friction brake system of non-driven axle will start. What is meant by non-driven axle? And fourth one is like driven axle will apply. This is the case of parallel regenerative braking. So what it means non-driven axle, say for example, we have a passenger car, we have front two wheels, rear two wheels. If we place the engine, if we place the motor, drive unit, everything in the front side only, it is called front driven axle, front driven vehicle. If we place the motor on all these other drive components on the rear wheel, then it is called rear drive vehicle. So whichever is called is the driven vehicle, driven axle, that application, the brake is not applied there. First, the non-driven axle. Say for example, if we are having a car where the motor, drive unit, everything is placed in the front. So front is driven axle, the rear one is, so the front is driven, what is the driving axle, and that is actually the driven axle, and the rear one is the non-driven axle. It is just following the front wheel, right? So in this case, first the friction brakes of rear wheel, that means the non-driven axle will be applied, and then the friction brakes of driven axle, that is the front axle, will be applied. So this is the parallel regenerative braking where it combines. But in this case, the serial regenerative braking, first initially the full braking condition, full braking torque is developed by compression regeneration. That means just by leaving the accelerator, whatever the regeneration torque, and then service regeneration driven axle on the driven axle side. So whatever the driven axle, that means the front wheel, there only the motor is there, right? So the service regeneration means where it will applicable. It is applicable only for the axle where the motor is there. If there is no motor in the rear axle, then it cannot perform the regeneration braking. Regeneration braking is nothing but it is something which relates the motor to the system. So wherever the motor is present, whether it is a front or rear, that will become the service regen driven axle, right? So that is how the operation in series braking, what happens is the two series or is a regenerative braking is applied. If the torque, if the brake torque applied on the vehicle is not sufficient, then only your friction brake system will get into prevention. But in this case, in parallel braking, during applying stage itself, after during still attaining the certain brake torque, it will be a combination. A brake for attaining such a brake torque, there will be a combination of both the friction brake as well as service brake together. So this is the case of a parallel and serial regenerative braking. So different companies, they adopt different regenerative braking strategy, and there are many challenges in this particular domain, and it is a very good. So since I say very much challenging, right? That means what? There is a very good scope for research scholars and faculty members, to do a lot of improvement in this particular area. Even as a student also, they can focus on their projects to improve. A small bit of efficiency, if they improve, that itself is a great achievement. So right now, many companies, to be in a safer side, they are not extracting, they are not investing, or they are not working too much on the regenerative braking to mainly to reduce the development time and all, because today the market has become very competitive. right? So if Tesla is launching a new car, immediately there is a huge pressure on Mercedes and other brands. They have to launch their car immediately. So likewise, the competition is very, very high right now. So they cannot spend too much of time on something which will give benefit, but in the later stage, they cannot spend too much time. So today, all the manufacturers on the research side, yes, definitely they are working, but still on the practical application, like there is a very small amount of efficiency being utilized in the regenerative braking, right? So let us understand the challenges inside this. So for example, one of the major area where a research scholar can focus is basically to develop a vehicle state estimator. See, one of the main challenge in regenerative braking is actually for the following things which I'm going to list now. See, one of the main challenges, first thing is to calculate what is the required braking torque, right? Say, for example, if the vehicle is traveling at 100 km/h, and immediately if I'm going to apply the full brake potential, right? How much amount of braking torque has to be generated in order to stop the vehicle from 100 to 0? So that is a very important factor, right? The braking torque requirement from the vehicle, right? So because, and now the next thing that we need to understand is, if we know the braking torque required, right? Now what we can do, we can compare that with the regeneration torque capability of the motor. So our electric motor which we have in the electric vehicle, either it is a two-wheeler, three-wheeler, or a passenger car, every motor has its own limitation. It cannot recover all the energy. It cannot keep on generating, right? Similar to the positive side of the torque, similarly for the negative side, that means negative minus level torque also, there is a limitation. So every motor, depend upon its capability, there is some maximum regeneration torque possibility from the motor. So when we calculate the braking torque required from the vehicle to stop for a condition, immediately the control system should compare that with the maximum regenerative torque capability of the motor. So now from this comparison, it will be very clear whether the regenerative braking torque capability is more or less. So now it is very simple. If it is more, if the regenerative regenerative torque that could be developed by the electric motor which is working as a generator is higher than the braking torque required to stop the vehicle, in this case, what will happen?
Only regenerative brake will apply.
Yes, in this case, the controller will decide the brake application completely with regenerative braking itself. Now, another condition. Now, at this point of time, the SOC is another important factor that we have to understand. The state of charge. Now, consider that now the SOC is already 80% more than 80%. Now, what do you think? Whether the braking will happen only with regenerative braking?
Battery is in the charged status, so service brake also will be applied.
So that means you are telling regenerative braking will also be there, service brake will also be there. Is it?
What is the charging status? Is it 80% or above?
It is like in a more fully charged condition, you can consider.
Okay,
Almost fully charged condition.
charge is almost full, means no additional charging is required for the
Yes.
battery.
So when the battery is already almost it's reasonably charged and more than 80% means with regenerative braking, this will actually heat the battery. Instead of just charging, it will charge the battery, but no issues. But in addition to that, it will also heat up the battery. So in order to avoid the temperature rise in the battery, because the temperature rise will be very quick, that is not good for a battery system, right? So in order to avoid such kind of behavior, thermal behavior on the battery system, many times the control strategy will be in such a way that if there is a more than certain limit of SOC, the battery will not charge, the regenerative braking will not function, you can say, right? It's all depend upon strategy. There is nothing common, there is nothing fixed for any system. It all depends upon vehicle to vehicle. So end of the day, the requirement is to have a controller, a control strategy or a control algorithm which will consider all these factors. So here what I want to explain all the people is what are all the factors that it actually takes into consideration by when we are designing a control strategy or a control algorithm for the regenerative braking, right? For example, it takes the input from the steering, right? It takes the input from the yaw rate. I think people might be aware about yaw. It's a sensor, basically sensor input. It talks this sensor, this yaw rate is nothing but how much stable your vehicle is, right? Whether your vehicle is stable or not, whether your vehicle is running in a flat, proper, stable condition, or it is like waving here and there. So the yaw rate input, that is one more important input from the for the controller. And the wheel speed as like a ABS, as like a anti-lock braking system. This regenerative braking controller as well need a wheel speed sensor input, and we also need the wheel forces input as well. This input we can generate from the motor, right? Depending upon the motor speed, the total torque, the force can be generated from there. That information is very easy to get, right? So these are all the information that is required for the controller, because say if now the regenerative braking is applied. After application of regenerative braking, within few seconds, the vehicle is started shaking. There is a yaw rate, there is a yaw happening in the vehicle, and because of that, there is a slip factor coming in front. Now what will happen? Immediately the controller should decide that to either reduce the regenerative braking or to increase the friction braking strategy. So friction braking percentage. So this is called, we call it as brake blending. We call it as brake blending. So the one of the main challenge in regenerative braking is actually blending the regenerative braking as well as the friction braking. That is the main challenge. So which is the one of the main factor that decides that is the slip, the wheel slip. So the wheel slip, according to the wheel slip, which decides the yaw rate and other factors, according to the steering condition, whether it is in a whether the vehicle is shaking. Because I think if people are from mechanical background, you will be very clearly knowing that when we apply front brake only, what will happen is the rear wheel, the rear two wheels, they will start waving like left and right. Right? And similarly, if we apply only rear brake, then left wheel will behave in a different way. So there should be a balance between the front and the rear wheel. It is not 50-50 balance, I'm telling, but there should be a percentage difference, a percentage balance between these two, so that the braking can be like a proper balanced braking can be achieved. So basically, when for a conventional vehicle, you take a petrol, diesel vehicle or electric vehicle, which axle will need more braking force? Either front axle or rear axle? Which axle that do you think will need more braking force or braking torque?
Where we have driving connections.
Is it so?
Pardon, could you please pardon the question, sir?
Yes. See, if we are having a front wheel, two wheels and rear two wheels, when we apply brake, where the braking torque requirement will be more, either the front wheel or the rear wheel? With irrespect of the drive condition, irrespect of placement of all these components. Just thinking from a vehicle dynamics perspective. What about the load transfer? Say if there is a 50% weight in the front axle, 50% weight in the rear axle, when I apply the brake, what will be the percentage change? Some of the weight from the rear axle will transfer to the front, right? During a braking condition, there is a load transfer that is actually happening from the rear side of the vehicle to the front side of the vehicle. That is why all of us, whenever we apply the brake, we all move front. Correct? That is the condition. So there is a load transfer, that is a weight transfer happening from the rear side to the front side. That means if the front side is having 50% weight and rear is having 50% weight in normal condition, during braking condition, the front wheel will have 70% weight and rear will have 30% weight, or the front will have 80% weight, rear will have 20% weight, depending upon how much amount of braking is being generated there. Right? If it is a very sudden braking, sudden braking condition, then there will be huge load transfer happening from the rear to the end. So end of the day, it is the front axle. Either we have the motor there, inverter there, battery, all these things, leave that. If it is a front axle, obviously the front axle will need more amount of braking torque compared to the rear wheel braking torque. You can try the same even with a two-wheeler. Check it and see how much load is getting transferred from the rear to the front during a braking scenario. And similarly, during an acceleration condition, if we are accelerating from 0 to 100, immediately there will be a load transfer happening from front to rear. So this is the load transfer which is happening during the dynamic condition, right? So
Correct.
basically yes. So when we have a vehicle state estimator, basically we should, there is a demand for such a component in the market, which can take inputs like steering input, yaw rate input, wheel speed input, wheel forces, all these inputs, and the controller present here should be able to calculate what is the amount of regenerative braking torque that can be supplied by the motor, or the amount of brake blending that can be carried out between the friction brake and the regenerative braking. And here it is actually integratedly working with the ABS system. So based upon the signals provided by this vehicle state estimator, the ABS system will either reduce the friction braking scenario, or it will increase the friction braking content depending upon the inputs from this vehicle state estimator. So that is a very good this is a very good area to work on, on the regenerative braking side as a project or a research project as well, right? And this is applicable for all levels of a vehicle, either it is a two-wheeler or a three-wheeler. But many times the challenge is with a heavier vehicle, there will be more capability to regenerate, right? As we know, there will be more potential, there will be a lot of energy available for a heavy vehicle compared to a light vehicle. So compared to a two-wheeler, obviously a truck and bus has more potential to improve the to extract more energy from the system, right? And you can see in this case, this is basically a example of implementation of serial and regenerative braking. In this case, this flow chart explains you the implementation methodology. For example, when there is a brake pedal input, so the required brake torque it's been calculated, and now the algorithm will check if SOC value, check the SOC value. If the SOC value is greater than 80%, if it is yes, then 70% of the front will be using front friction brake, and 30% for the rear friction brake. There will be no regenerative braking applied. Is it clear? Say for example, in this algorithm, if the SOC is 80% and more, if it is yes, then 70-30 split is happening. 70 for the front wheel, 30% for the rear wheel, but both are friction brakes, conventional friction brakes. If the answer is no, if the SOC is not greater than 80%, if that is the condition, then the algorithm will check whether the total braking torque is less than the maximum regenerating torque. In this case, what will happen? If in case the answer for this is no, if the total braking torque it is not less than or equal to the maximum regenerative torque, then what will happen? If we apply regenerative braking, what will happen?
It is not sufficient to stop the vehicle.
Yes, simple. So it is not sufficient to stop the vehicle. So obviously it will need the support from the friction braking torque, right? So if the answer is yes for this condition, then yes, fully regenerative braking is applied. And if it is no, if that is the answer for in the algorithm, then it will ask another question. If 70% of the total regenerative braking torque, total braking torque is less than, whether that is less than the maximum regenerative braking torque, right? If in this case, if the answer is yes, then 70% of regenerative braking will be applied on the front wheel, and on the rear wheel 30% of the rear friction brakes will be applied. So here the front friction brakes will not work. That means the ABS will not operate the two front friction brakes. Only the regenerative braking will happen there. But in this case, if the answer is no, in this case, the front wheel will be like, if it is not less than the maximum regenerative braking torque, 70% is not less than the, or I can say the other way also, maximum regenerative torque is actually greater than 70%. Then in this case, you can see that it is a combination, the maximum regenerative torque that is possible by the vehicle plus friction brake torque possible in the vehicle is equal to totally the 70% of braking torque, and the rear wheel as usual 30% of the friction braking will be applied. So end of the day, at any point of time, you can see that other than the SOC related problem, at any point of time, regenerative braking is being applied at a specific condition, right? But in this case, in a parallel regenerative braking, if you look at this condition, If you look at here, the SOC is 80%. If that is the case, or at the same time, the maximum regenerative braking is actually the total braking torque is less than the regenerative braking. Even in this case, on all these cases, 70% of the braking torque for the front, it's provided with the front friction brake, and 30% is provided with the rear friction brake. So here the more, the utilization is mostly from the in parallel braking, the utilization is mostly from the friction brake, and very small amount of regenerative braking will be applied in the case of that too, if the regenerative braking torque is available, right? So that is the difference between the serial and parallel. So parallel regenerative braking, it gives more importance to actually apply both the friction brake and the regenerative braking. But serial braking, when we say serial braking, the first priority, it checks whether it is possible to fully apply the brake with regeneration. If it is not possible, at least second step, it tries for partial regeneration. If it is not at all possible, then only it might go for the full, it will go for at least partial friction, partial regeneration, and then rear wheel friction condition. So different sort of implementations are possible in a serial and parallel regenerative braking, and both this thing, serial regenerative braking, it has the ability to gain up to 25% of the energy recovery possible, right? And in the case of parallel braking, only 15 to 18% of energy is required from the system. I'll show the energy values, the whatever values basically, right? So this is a kind of a strategy. So today, as a student or research scholar, the areas are like control strategy development, control algorithm. Basically, we can build a control algorithm which can be based upon a serial braking or parallel braking, or it can be even combined with the advanced topics like the stability control and emergency braking assistance. There are many scope of research in this particular area of regenerative braking. And specifically speaking, India based research, very few people have done it, especially in IIT Madras. We have Mr. Dr. Ram. He is working mainly on the regenerative braking area. So very few people, we can name him very easily. So very few people are working in this area throughout India. So India level, such a huge country, but the area of focus of research on regenerative braking is very limited. So definitely, I would encourage the faculties either from electrical, electronic background, mechanical, mechatronics background to contribute in this particular area of research, since there is a huge scope for improvement, right? And definitely, it will be immediately responded by the companies as well. If you do any improvement on the regenerative braking using as a new controller or strategy, definitely that will be encouraged by the manufacturer. If you do, once you do some developmental work, automatically you will be able to get some projects, funded projects from the manufacturers. So already we are working with Ampere vehicles based out in Coimbatore. We have our micro office actually. We have our micro R&D center at Hindustan institutions in Coimbatore. So we are actually doing some kind of related activities, planning more activities in the coming future. So I would recommend a similar way, to extract projects from the companies. So before that, we need to do some project, right? Then only they can trust and provide us. So maybe if already someone working on regenerative braking, kindly let me know so that I can see where I can bridge with you guys. Otherwise, you can also let me know if you need any support in the regenerative braking side. So anyway, this is an example, a case study. So in this case study, we will take an example vehicle, and we will see what is the regeneration potential of this particular vehicle of a certain weight and other characteristics. For example, the vehicle characteristics are showcased here. Motor characteristics are showcased here. So this is the example we are taking for this particular case study, right? So the mass of the vehicle that we are taking for the case study is 1,325 kilogram, and the frontal area of this vehicle is 2.57 meters square. All these factors, why they are here? Because they are all the factors which actually influences the braking scenario of a vehicle, right? So they influence the vehicle a lot on its braking condition. That's why we need to consider all these factors: the mass of the vehicle, frontal area, drag coefficient, air density, radius of the wheel, rolling resistance coefficient value. So this is a small passenger car vehicle with these vehicle characteristics, and these are the motor characteristics which are used in this particular vehicle. So the power of the motor is 40 kilowatt. The maximum current capability is 400 ampere. minimum maximum minimum voltage 60 volt, and maximum motor torque is 520.88 Newton meter, and maximum regenerative torque is 322.7. Right? It doesn't mean that if the motor is having 520.88 as maximum motor torque, it doesn't mean that same torque is applicable for regeneration as well. No. So there is a lot of restriction on the regeneration. And can any participant tell me what are all the factors that actually restricts the maximum regenerative torque? Let us see your understanding on a system level. What do you think these are the factors that actually limits the regenerative braking torque of an electric motor? Any idea? Any inputs here? Yes, please. Any inputs?
Sir, during the regenerative mode, actually we are applying kinetic energy to the rotor only, na sir?
Yes, yes, yes.
So
See, the motor's positive torque is very high. It is close to 520.8, but on the regenerative side, it is not able to, achieve more torque. What do you think is the restriction behind it? It might not be only the reason behind it, might not be only the motor. It can also be the other components which is actually transferring the power. Can you tell the power flow from where the power flow?
Yes, sir. So actually, in the gear ratio, it is in the reverse mode. It is operating.
Yes. Okay.
Normally, whether suppose it is going in the first gear or second gear or third gear.
Okay.
So during the regenerative cycle, it is power is transferring the reverse mode.
Reverse operation. Yes. Okay.
So there will be a lot of gear trains.
Okay.
So one will be a driving gear and another one will be a driven gear. So during the reverse mode, driven gear will be.
But the thing which is explained here, this is only for the motor, the ability of the motor alone. So the motor itself is not able to regenerate the created torque which more than this. So I think it is not the gear is something which is additional, which is actually which is further reducing this torque. But this is a capability of the motor alone.
I don't know, sir.
Yes. So we look at in the reverse direction. Before the motor, what is there? We have the inverter and we have the battery. So it is basically not only the motor regenerative torque, it is dependent on multiple factors. One is how much amount of what is the capability of the inverter that we have in the system that can handle the current in the opposite direction. So we have a positive current in the when we are running in the positive side, right? But as we know, all these components are bidirectional. We have the inverter component system are bidirectional, but still they have their limitations to work in a bidirectional mode, right? They can't function in the same way as on the both bidirectionally they can function in the same way. So there is a limitations on the MOSFETs. There are limitations on the switching devices, as I mentioned, limitations on the capacitors, limitations on the converter, all these limitations. In addition to that, the motor, when it is operating in a short span of time, it is also has the limitation to develop a maximum regenerative torque. The time, end of the day, there should be a sufficient time to develop a torque. So in this case, the time availability to generate a torque for a motor for a braking condition, it will be very short, so that it may not be able to reach its maximum regenerative capability. So it is definitely affected by multiple factors. The regenerative torque of the motor is affected by multiple factors. So even as a motor design engineer, they also try to improve this capability. So if we improve this capability, what is the benefit? If we improve the regenerative torque of the motor, then what is the benefit?
Entire braking force we can utilize from the regenerative braking.
Yes. So we can extend the regeneration region of the vehicle. and we can try to recuperate more and more energy. So that is the need of the hour right now. As I told, 25% of energy recovery possible. So it is something, it's a very huge value. It is not say 1-2% means okay, we can accept. Yes, so we cannot, it is not such much significant value. But 25%, it can improve the efficiency of the system means, it can improve the range of a vehicle means, then it is definitely, there is a huge potential on the system. So it is completely dependent on what is the ability of the motor to recuperate that, and it is also other important factors. As you mentioned, the gears, they also contribute on the losses, right? As you mentioned, yes, during the regenerative braking, if the number of gears are more, obviously they will also become a resistance, they will consume some of the energy. But in electric vehicle, as I mentioned, there will be not more than 2 gears, worst case. Only in few vehicle, the video which you saw, the video which you saw, the Audi e-tron, that is actually a 4-wheel drive vehicle, and that vehicle is completely different from a conventional electric vehicle. So Audi e-tron, it is a 4-wheel drive vehicle, it is a performance vehicle which is having a huge torque requirement. It's like more than 400 Newton meter torque. That is very huge actually. So in such cases the torque, in that cases the gears will be obviously more, because for meeting the overall performance requirement. It's a performance vehicle. But if we take a conventional sedan, a conventional electric car, hatchback car, sedan car, the number of gear usage will be almost avoided. So there will be 1 or 2, maximum 2 gear. Most of the vehicles have single reduction gear only. So that is the benefit of using electric vehicle. If we use the same number of gears like petrol diesel vehicle, then there is no benefit it is actually providing us, right? So the number of gears are obviously lesser in electric vehicle. So in this case study, in this scenario, these are all the specifications that you have seen, and this is the performance. The voltage level of the cell, the battery system goes from 9.5 to 12 voltage, and the SOC variation you can see. The SOC variation from 0% to the variation of the SOC, and the SOC variation with respect to internal resistance. So how the internal resistance behavior is there for a battery system with respect to SOC, right? SOC change. So SOC gets increased. The state of charge increases automatically whenever the regenerative braking is applied, right? So tomorrow when we are looking at the model based simulation using MATLAB Simulink, I will showcase the real time readings. How the SOC variation affect the other factors inside the battery, like voltage, internal resistance, and all. Right. So let us take 4 cases here. First case, 4-wheel braking at small deceleration. Now we are going to imagine 4 different conditions. First condition is the vehicle is running in a city traffic, and it is like a small deceleration. Stop, start, stop, start, stop, start, like that. The behavior is there. In this condition, for this particular vehicle of this specification, what is the potential of regeneration? Let us understand here. Consider an all-wheel drive vehicle. Suppose you can say the rest from 25 meter per second to a deceleration of -3 meter per second square. So this is the deceleration rate. And now what is the required braking force? How to calculate it? Just take the weight of the vehicle, right? We have to take the weight of the vehicle and multiply with the deceleration value, right? And then use the, you can take the value from, this is the speed at which the vehicle is resting from. So from this 25 meter per second to 0 meter per second, that is where it is going to come. So if we calculate the required braking force, what we are able to get is around 3000 minus 3620 T, 620.43 Newton. That is the braking force required in the opposite direction to stop the vehicle. So if we divide this braking force on all the 4 wheels, then it is like 905.10 Newton for each wheel. So now the question is whether the regenerative braking system could support this. So the regenerative braking torque per wheel in this case is, it is close to 270, that means 30%, right? 30%, if that is the 30% is the braking force applied, minus 271. So since and what is the regenerative braking capability? 322.7 is the maximum regenerative torque possible by this motor. So the required brake torque is actually 271.53. Since the required braking torque per wheel is below the maximum regenerative torque capable of the generator, so braking can fully regenerative depending upon the braking strategy applied. So it can be, the overall braking, the scenario, braking scenario can be either full regenerative braking or possible, because it is actually less than the capability. It is the total braking force required, actually it is less than the capability of the system. So it is obviously able to do that. If it is the case two, in the case two, it is a large deceleration. So now the vehicle is having a large deceleration. So the vehicle is now, instead of decelerating at 3 meter per second square, minus 3 meter per second square, now the deceleration is minus 8 meter per second square. In this case, the total amount of regenerative torque, that means total amount of braking torque, the force per wheel requirement is actually 2561.35. And if it is like, and if we calculate the required braking torque per wheel, in that case, it is 768.40. So in this case, 768 is actually greater than what the motor can deliver. The motor can deliver only 322.7. So in this case, complete regenerative braking is not possible. So the braking torque per wheel is above the maximum regenerative torque capability of the generator. So braking cannot be fully regenerative. Hence, friction braking is applied in combination with the regeneration. So this is a case where regeneration braking plus friction braking will be applied. That is the third case, a maximum deceleration possible with the regenerative braking. How to calculate the maximum deceleration possible with regenerative braking in a case of a vehicle, this particular vehicle. So in this case, how to calculate it? So if we have the values of total longitudinal force applied on the wheel, and what is the coefficient of rolling resistance, what is the weight of the vehicle, and what is the acceleration due to gravity, if everything is considered, then we can calculate the maximum deceleration possible by the vehicle with regenerative braking. So what is the maximum value it can handle is minus 3.43 meter per second square. So it can be understood that for a harder braking, purely regenerative braking would fail to give a desired deceleration. So when we have a very high sort of deceleration, obviously the regenerative braking alone cannot support that complete performance requirement. So that is one of the challenge, actually. If you look at the simulation model, the same condition, these three cases are actually run in a simulation, in a MATLAB simulation, and you can look at the simulation results, how the outcome has been there in the, I'll show the simulation models for the same, but right now the results, when you look at the results, right? So look at the brake pedal velocity, brake pedal input. Basically, the brake pedal input is provided at a time of 10 seconds after from where we are actually applying the brake. So brake pedal input is coming, and till the time you can see the velocity of the vehicle, it is actually forward direction. And once we apply the brake, the velocity starts coming down. So this is the velocity plot for the serial regenerative braking, and this is the brake torque. You can see the brake torque. Do you remember the first case, small brake pedal input? If you remember the value, that was actually the total braking torque required per wheel was actually lesser than the capability of the motor, regeneration capability of the motor. So because of that, complete brake is actually applied by front regeneration braking only. So you can say immediately after 10 seconds, immediately the full braking force was applied by the regenerative braking itself, and friction brake did not function here. It is a serial braking condition. And in this case, look at the variation in the SOC. You can see that for the first 10 seconds, it has reached to 0.7. You can say it's below 0.79, and within a span of few seconds, the SOC has changed from 0.79 to 0.8, right? Almost 0.8. So this is the variation happening in the SOC, right? Almost 0.1 a percentage of SOC has been increased in this particular short braking condition. It's a serial condition, serial braking condition. And if it is a parallel braking condition, in this case, what will happen is immediately after the 10 second duration, when the braking is applied, immediately the front friction brake will be applying and rear friction brake will be applied. And in this case, mostly the combination is not, initially the more importance or priority is given to the friction brakes only compared to the regenerative braking. If in case additional requirement was there, in that case only the regenerative braking might function. So overall, the SOC, there is no change in the SOC on the parallel regenerative braking, because what is the reason? What is the reason, do you think, in the parallel regenerative braking was not deployed? Why? What is the reason? because the vehicle is actually having a small brake pedal input. The overall deceleration rate, the deceleration rate is very small, that it is not going to give much benefit to the regenerative braking environment. That is why you can see the point one means, in this case, the parallel regenerative braking, the controller considers that as a very, very lesser amount of energy recuperation. So it is not giving importance in that case. So it is only deploying the front and rear friction brakes in this case. But whereas if it is a full brake pedal input, right? If it is a full brake pedal input, in this case, if you look at the serial and parallel braking condition, right? Both the cases, regenerative braking will be applied. Let us look at it. Say if you look at the 10-second duration, this is a full brake pedal input. It is not a small brake pedal input. It is a complete deceleration input given here. And look at the deceleration value. It is close to 5. It is very high value compared to the previous model. It is just 0.7 meter per second square. But in the new model, that means the new case. In this case, it is minus 5.8 meter per second square. Such a high level of deceleration at this case. Right. So in this case, what will happen immediately after 10 seconds, the full brake pedal input is achieved. How it is achieved? It is first initiated with regenerative braking, and then since it is not sufficient with regenerative braking, rear friction brake is applied. What? Rear friction brake. And then after rear friction brake is applied, then only the front friction brake is applied. Look at this is the zoomed area. This picture is actually nothing but the zoomed area of this area. You can say first within 10 seconds, first the regeneration braking is applied. After 10 seconds, 10.1, before 10.1 second, since the controller comes to know that the braking torque is not sufficient to stop the vehicle, immediately the rear friction brake is applied as the sequence. This is the sequence. And after the rear braking is applied, after 10.1 second, then only we have the front friction brake applied. And overall, the front friction brake, because as we know, front brake is the front wheel is where more amount of braking torque is actually required. So the front braking torque will be like the braking torque will be more obviously compared to the rear one, right? That is where and finally within a span of 10 to 12 seconds, within a span of 2-3 seconds, we are able to reach the maximum deceleration force to stop the vehicle, and the vehicle comes to the rest position. Right. So, and we look at the SOC variation. In this case, the SOC variation is very nominal. You can see in this case, look at this case, because the amount of regenerative braking applied is very partial, because a major amount of force is actually applied by front and rear braking force, because it is in this case, it all depends upon the strategy. In this particular case, they have applied this strategy. So it maybe depend upon the SOC and other factors, right? So if the SOC, depending upon the SOC, we can also see more amount of regeneration capability. So for example, in this case, the parallel braking condition, first the braking is actually applied with front friction brake, and front friction brake, it is actually giving a brake torque, and immediately after reaching a speed of 10.1, after a time of 1.1 second, immediately the regenerative braking system also comes into picture. So now combination of front brake, rear brake, and the regeneration, but regeneration did not started at this initial stage. That is what the difference. So on the serial braking, it is actually starting with the regeneration. So the first braking action is actually performed by the regenerative braking, whereas in the parallel braking, the first braking condition is actually considered from the front and rear friction brake, and then if they see a potential to regenerate, then they are additionally adding the regenerative braking to reduce the stress or the amount of usage. This completely depends upon the SOC of the battery and other performance requirements, whatever the limitations, the factors that limits the battery performance, all these things will be taken into consider whether to have a regeneration braking or not. So this is a different condition. So if it is a partial braking, partial 50% of the brake applied, if that is the condition, then in that case, in that case, you can see the serial regenerative braking is also provided, and then parallel regenerative braking is also provided, and you can see the frictional braking only and regenerative only. So if we use these four different braking conditions at a partial braking event, which is having highest potential, obviously regenerative only will have a more potential to increase the SOC, and then serial regenerative braking has another next level of potential for regeneration, and next to the parallel regenerative braking. So all these, this is the level of a different braking scenario. So completely depend upon the vehicle speed, depending upon the strategy that we are going to implement, depending upon the amount of brake force applied by the driver. There are multiple driving factors from multiple directions. So it is up to the development team to decide which factor they are going to give preference and more importance. And they also should balance the the overall performance. They should balance both SOC requirements and all this thing they meet. At the same time, they should not create a vibration or shake or any disturbance for the driver. Telling that we are going to generate, will a customer will accept it? Whether a customer will accept if there is a huge amount of vibration on the vehicle during a regenerative braking? No, the customer will definitely not encourage energy recuperation at the cost of losing his convenience or comfort. Definitely it is not possible. So from a customer perspective, is the first way a manufacturer will think, obviously. So energy recovery is obviously a secondary factor. A customer should not feel, the passenger or the driver should not feel any sort of disturbance basically during a braking action. So end of the day, it is the serial regenerative braking which is having more capability, more capability to actually to recover more energy compared to the parallel regenerative braking. So today most of the manufacturers, they apply serial regenerative braking, but at the cost of only thing is, if they are very sure that the blending, if they are very sure that the serial regenerative braking could stop, but we cannot do so. We cannot completely depend on the regenerative braking, because the regulation or European regulation, what we shown today, last previous slides, that is actually limiting the amount of that means the amount of regenerative braking, or you can say it is actually giving that, it is telling that the braking friction force, the friction braking torque, it should be given more priority compared to a regenerative braking. If it is the regenerative braking, if you think regenerative braking itself will be able to provide it, support it, then in that case it can be applied with a by-wire system. So I think people will be knowing about brake-by-wire technology, right? Which is actually implementing in coming nowadays in the new vehicles. It is already implemented in the other countries. In India, it is like one by one they are coming in different models, right? So the thing is, actually we need to have a higher, the brake-by-wire means without any sort of hydraulic all this activity, the control will be completely based upon the brake pedal, brake control will be completely based upon by-wire technology. So it will be a signal will be transferred from without any wireless, using a wireless technology. That means by wire way, we will be able to instead of a physical, mechanical connection between the system, there will be a physical electronic signal which will be transferred from the actuator to the brake actuator, from the signal provider to the actuator. So basically, that is the brake wire technology. In future, we will see many vehicles with the brake wire technology, and in such cases, the challenges are going to be definitely more. And but the usage of regenerative braking with brake wire technology will be more easier, since all are already everything is electrical electronic component. So in that case, the potential to regenerate more amount of energy, it will be much better. So one of the main area of work today, that if you look at the job market today in the regenerative braking domain, modeling and development, model-based development has a good scope. And in this particular case study also, they have developed a model. This is actually the complete vehicle model. Let me zoom it so that you can have some amount of understanding what are all the, basically develop this vehicle model, vehicle level model. It is completely an automotive engineer or a mechanical engineer's role, because all are like the components which are present here as at the vehicle model development. It is all related to suspension, steering, braking, wheels, tires. So it's all coming under the vehicle dynamics part. So in addition to that, there will be some amount of body sensors. If you remember the yaw rate signal, which is nothing but coming from the sensor only. So we need to place the yaw sensors at different point of position, and we need to, as a vehicle model. So the four wheels basically, wheel 1, wheel 2, wheel 3, V4. So totally 4 wheels. That is what actually shown here. I don't think it is a very complex model. So just they have just converted a vehicle wheel drive system into a model. That's it, right? So and they have placed the bearings, body sensor, and they are actually totally 2 body sensors are placed at this point, and one is on the front side and one is on the rear side. So they are checking the yaw rate on the front axle and yaw rate on the rear side. So basically to decide which side braking should be applied more, whether the front side or the braking rear side, right? If you remember the racing cars, if you remember the racing cars, in the racing cars, formula cars and all, the engine, all the component will be on the rear side of the vehicle. So more weight will be on the rear side and more weight will be on the less weight on the front side. So the weight distribution is different from a formula car and a passenger car and a sports car. So depending upon the weight distribution, the amount of force distribution, brake force distribution will also automatically vary, right? And when you look at this case, this is the model that they have used for the braking. So this is the serial regenerative braking model, and this is the parallel regenerative braking model. When you look at the model, let me zoom this. You can clearly see that the maximum regenerative torque available. So this is basically a lookup table. So before developing the model, what they are actually doing is they are bringing up the region. What do you say? They are bringing the lookup table inside, which is actually we can receive the lookup table based upon the manufacturer specification. So basically the manufacturer, when you ask the motor manufacturer, he will provide you this lookup table, the chart or the Excel sheet of or the graphical data, basically, or from the graphical data you can plot it into an Excel sheet and you can upload that into the MATLAB simulating environment. So we can have the maximum regenerative torque availability lookup table, and based on which the brake torque, brake torque and the regenerative torque, both are, you can see both are actually combined here. So it will be subtracting the maximum regenerative torque and the brake torque, and if it based upon the value, if it is greater than 0, whether it is positive or negative, it will decide whether to go for full regenerative braking or partial regenerative braking, right? That is the model showcases. And you can see based upon the decision it makes, it decides whether 70% of the same thing, this algorithm what we developed there, the strategy which we saw there, same thing is actually converted into a model, and that's where the simulation has been performed. So that 70% front brake split and 30% rear brake split. So they are splitting both these brake split accordingly, and finally the front friction braking, rear friction braking, depending upon the requirement they do that, right? And finally the brake regeneration torque possibility, and finally the overall brake torque achieved either with regeneration or the friction braking. So this is the serial braking condition. And if it is a parallel braking condition, then both the, in this case, both parallelly serial braking, that means friction braking, regenerative braking, both are considered. But in this case, look at the values here. If the brake torque value is less than or equal to the maximum regeneration torque, or if the value is greater than the maximum motor generation torque, so based upon the comparison, both the values parallelly, it decides whether to have a combination. First it will start with the regenerative friction braking, and then it decides how much amount of regeneration should be done and how much amount of regeneration force to be applied. So the overall, the model will calculate the balance between the friction brake and the regenerative braking. That's the overall model motto of the background model. So overall, if you summarize the whole developmental activity in this area, serial regenerative braking provides maximum energy recuperation compared to a parallel regenerative braking. And in this case study, the case study taken from here, the overall case study, if they run the simulation, they have run the simulation in a NEDC cycle, which is actually a driving cycle, right? So have anyone used any driving cycle previously? Driving cycle for any simulation or anything? Or if you people already know what is meant by a driving cycle? Any idea? Okay, let me explain that better, so that, because it is a very key component of the overall performance testing. However, we'll be talking about the driving cycle tomorrow as well. Let me show the picture and just try to explain you a bit about it. Say for example, so what is this? Basically, it is nothing but It is nothing but the vehicle speed. The y-axis is vehicle speed, and x-axis is nothing but it is actually the time, the overall time it is taking. Say for example, now we are traveling from, for example, if you are traveling from Thrissur to Palakkad. Say for example, if I am traveling to Thrissur to Palakkad, during this whole journey from Thrissur to Palakkad, I will be applying acceleration sometime. There will be some braking condition, and there will be some traffic signal. So I will be in idling condition. So acceleration, brake, acceleration, brake, acceleration, idling, acceleration, brake. So combination of acceleration, braking, idling, acceleration, braking, idling. So for a certain distance covered in a certain distance, we will have a combination of acceleration behavior, deceleration, braking behavior, and stable, what is idle behavior, right? This is called as a driving cycle. So this simulation, what they have done is they have run this, this overall model inside this driving cycle called NEDC, and based upon that driving cycle running, say imagine like we have developed this regenerative braking and we have fitted that in a vehicle, and we are traveling from Palakkad to Thrissur. If we are doing the test in this case, there will be some amount of energy recovery, right? There will be some amount of energy recovery. Total kinetic energy during braking in a NEDC cycle is almost 1.75 megajoule. That is the simulation result. Total kinetic energy availability in a NEDC cycle, basically, right? And total electrical power recuperated with parallel regenerative braking is 0.52 megajoule, and total electric power recuperated with serial regenerative braking is actually 1.21 megajoule. And it is very clearly mentioned, clearly visible that serial regenerative braking, it is almost 69.68% of energy recovery compared to a parallel regenerative braking, which is maximum it can recover up to 30.25% of the total energy available. So it is very clear that with the amount of regenerative braking, serial regenerative braking can offer a range extension of 5.3 kilometers. And if it is parallel regenerative braking employed completely, then in that case, it can give a range extension of 2.3 kilometers at the same time following the ECE drive profile. So it is very clear that serial, what is more important is the temperature, the overall range extension. See, 5-kilometer range extension for such a small duration, for such a small duration, it is very definitely very positive factor. That is what I told. That is more if the vehicle is actually, so if the vehicle is having a 200 kilometer, like 200 kilometer range possibility, right? So 5-kilometer into, like, if for example it is 2.5%, right? If it for a 200 kilometer vehicle, it is almost 2.5% improvement on the range of the vehicle. So it is definitely depending upon the amount of percentage of recuperation, ability of the ability of the controller to timely activate the braking system, and ability of the motor inverter system to recuperate without any losses. All these factors can further improve the range extension more than 5 kilometers. So definitely 5-kilometer range extension is not something, it is definitely a significant value, right? What's your opinion, participants? 5.3-kilometer range extension, what do you think? Do you think, do you feel, do you see a potential behind regenerative braking?
Yes, definitely.
Yes. So obviously, depending upon that too, with a heavy vehicle, right? This is just for a small passenger car. If it is a heavy vehicle like trucks and buses, because in those cases, the vehicles will be very heavy, tons and tons. So in such a case, there will be huge potential to recover the energy. So with the simulation results, and obviously they are, I would strongly recommend to do both simulation as well as experimental verification. So to start with, I would suggest participants to take a two-wheeler. And that's how I did it actually. So I did a study on a two-wheeler, took some electric two-wheeler, just studied the total amount of current flow out of the system during the braking condition at different braking situations in a dynamometer, and we did the same. And finally, we I think in our test, I remember that we were able to see a potential to gain up to 7.5 kilometer range actually for a two-wheeler. It was a two-wheeler which was a 100-kilometer range already there. 7.5 kilometer means you can see the potential basically. So it is almost 7.5%, right, for this particular vehicle. So definitely it is very notable. So I see a huge potential in this area for further improvement and research. So the area of work as a research scholar or a faculty or a student, the area of focus could be to develop a better algorithm. So develop a better control strategy and develop a better blending methodology. How to blend both. As I told, we cannot compromise braking distance. With if I cannot say regenerative braking will be applied, but the vehicle will take more time to stop. No, it cannot be accepted. The vehicle should stop as per in time with as specified in the ECE regulation. Just go and download this ECE regulation. It is available in the website. Just go and type the regulation value ECE R13, right? What I mentioned. R13H or R13.11. The guidelines are provided there. So strictly we need to follow the guideline there. With respect to after following that, we need to see how much maximum recovery of energy possible. And at the end of the day, we need to try to optimize it further and further to increase it more and more for the future. So that's the level of work possibilities to work in this regenerative braking. So is there any questions from participants now? Is there any questions from the participants at this point of time? Any questions? So let me give time for more questions so we can discuss more on previous sessions as well, upcoming sessions as well. Throw your questions, whatever it may be. Now this is the time I'm providing for questions. So it has been a very long discussion. So even I will provide you, I will ask you a few questions as well from my side, kind of a quiz. But before that, if there are any questions about the session, any clarification needed, any participants? How many of you are like mechanical professionals here? Are there any mechanical? Okay. Mr. Sudesh, do you have any question? You have raised your hand.
Yes, no question, sir. I belong to mechanical. That is why I raised my hand.
Okay, okay.
I already discussed, asked my question, doubts, sir.
So, already, are you working with any regenerative braking project?
Not like that, sir. No, I am taking automobile engineering course. That is why I.
Okay. So, so did you understood what I said in this session today on the regenerative braking?
Yes, it was clearly understood, and it was very nice only, sir. As you said, we have a lot of scope, lot of scopes are there for the research, that algorithm, everything, that is blending of brakes, everything. It was very useful, sir.
Okay.
Okay,
Yeah. Thank you very much. So on the electrical front, any questions are there? Because when we say regenerative braking, people think, okay, this is not our area, right? It's not so. It is actually the complete EV is actually the role has to be played by all the engineers. So in this area also, the control algorithm development, even the control algorithm development actually, see, I'm a pure automobile engineer. So even I work in the control algorithm development area only. So it doesn't mean that it is an area for electrical electronic people. It's just understanding of the system. If we understand the system completely and properly, then obviously any engineer can develop an algorithm for that. So only thing is it needs some small amount of programming knowledge and then start doing things clearly. Mainly the system knowledge is very important. So any electrical electronic professional here, already working in regenerative braking or looking forward to work? Anyone want to give any inputs here? So it means right now no one is working in this particular area. Should I take it in that way? Okay. So there is a question from one of the participants: how to generate drive cycle in MATLAB? Is it using sim power tools or any other thing? Mr. Chandni has asked this question. See, it is a very, very simple activity. Adopting, bringing a driving cycle. Tomorrow I will show an example, but very simple. Just to, you should have a Excel sheet of the driving cycle. And in the MATLAB, in the MATLAB folders, I think when you install MATLAB, you will have MATLAB folder. And in that MATLAB folder, there is a dedicated folder for driving cycle. Let me show that if it is possible. Let me show that. So I have the MATLAB installed in my laptop. So let me just tomorrow we'll be discussing in detail, but let me show the driving cycle folder. Where you can actually upload it either through here, or you can even upload the Excel sheet directly. I think you might be aware about it, right? Uploading an Excel sheet into bringing an Excel sheet into MATLAB. Have you done it? It's a simple step, right? So I'm just searching for that folder. So we have a dedicated folder where the different driving cycles are being stored actually in MATLAB. So inside that folder, you can go and paste the Excel sheet that is possible. So otherwise, you can also import it directly. Using the Excel sheet, you can actually import it. You just need to put an Excel sheet with what are the two parameters, Chandni? Like, what are the two parameters in a driving cycle? What are the two parameters are there in a driving cycle, basically, Chandni?
So speed and time, acceleration rate.
Yes. So it's the vehicle acceleration, deceleration rate, and it is the overall time the way overall driving cycle is running, right? So for every
Yes.
overall timeline, how much is the variation? So just you need to plot that. I would strongly recommend you to visit this. Have this PDF copy. Wait a moment. Driving. Just go to Google and type a driving cycle PDF. Okay, you will see a book called Reference Book of Driving Cycles. So kindly download this book. It is an open access book which is available in the internet. See, this is the book, a reference book of driving cycles for use in measurement of on-road emissions. Right. So just download this book for you, and when you download this, you'll be able to see all the driving cycles. See, it is clearly shown. EADC. What is the total distance running? Totally 6 kilometer. Total time, driving time. So basically, it is the speed versus time, right? Speed versus time plot. So you have to create an Excel sheet on this, right? And sometimes the driving cycles are available in Excel sheet also. Okay, for example, if you want to have the WMTC driving cycle, just go to WMTC driving cycle Excel sheet. You will be able to get the Excel format file. Let me check if I have one. You can get it. Basically you can get it from the online.
Okay, sir.
So just you can go to MATLAB and import. When you import the Excel sheet, you just have an Excel sheet ready with you with the driving cycle, and just press import button. So it will automatically import it. See, this is the folder. This is the folder. On the MATLAB folder, you will have a reference folder. So basically here we have the driving cycle data and all. See, it is actually shown. The pictures are available here. So just go to MATLAB and just press import button, import the Excel sheet. That's the way you can import it. And once you import it, just store the, tomorrow when I open the model, I will show you, I will show you exactly where the location is there actually in the MATLAB model, right? So is there any more questions from the participants? Any other questions related to regenerative braking or any other case? So there are, like, we can even talk about regenerative braking for 10-15 days. Such a huge content is available from my side. So definitely in future, when we have such kind of dedicated sessions on each topic, that we'll be talking about that, for such people. So I hope session was quite useful for everyone. And if there is no more questions, then ma'am, over to you. So you can, Aparna ma'am, yes.
Okay, sir. Okay, so we have come to the end of today's session. I hope there are no more questions. We'll have the next session tomorrow morning at 9:30 a.m. Okay, thank you, sir. Thank you, participants.
Tomorrow we will be discussing about model-based simulation, model development and simulation. And on the second half, we will be we'll be talking about testing and certification, which is very interesting for understanding the testing applied, testing and certification procedure followed by a electric vehicle company. So all these things we will discuss in detail by tomorrow. So thank you all for your active presence.